In this video, we'll again be identifying the domain and the range of various functions, but we'll be looking at different types of graphs than we've looked at before. So just to remind ourselves of the vocabulary, the domain of a function is the set of all possible input values of that function, and is typically talking about all of the x values that we need to make the points on that graph, or all of the x values that we put into our function. The range, on the other hand, is the set of all of the possible output values of a function, or the y values that we use to make points on our graph, or the outputs that are a result of all of our input values. So these are the two vocab terms that you should be familiar with so that we can actually identify the domain and range of each function that we see. So let's take a look at this first example here. When I dive into this example, what I see is that I have two endpoints on this particular function. And if I see two endpoints, what that is telling me is that I'm going to have two inequalities in this domain and range representation, because each ending point represents an inequality. So if I have two endpoints, I'm going to have two inequalities somewhere in my statements. We're just going to keep a lookout for that as we work on finding this domain and range. So let's start with the domain. And remember, for the domain, we're looking at all of the possible x values that are needed in order to graph this function that we see on the screen. Well, when I look here, what I notice is that this first endpoint right here pairs with x is -5. So I know that that's an important point on my number line. So I'm going to go ahead and plot that point there. Then, when I take a look at the other side, what I notice is that the 3 for the x coordinates is also important because it pairs with the other endpoint there. And then I notice that the line of the graph is caught in between these two x values. And if you look carefully, what you'll notice is you don't need any of the x values on this side of the graph. Notice that there's nothing graph-wise over there. We don't need any of those x values. And we don't need any of the x values on this side of the graph. We only need the x values sandwiched between -5 and 3 in order to create our line with our two endpoints on it. So if we think about this in terms of a number line, the x values that we really need are sandwiched in between -5 and 3. They start at -5 and then they go all the way up to 3. And this is a situation where we have two inequalities because we have a compound inequality here. Notice that x is sandwiched between -5 and 3. And if we look at this carefully and we write it carefully, we can say that x in one statement is on the bigger side of -5. So notice that, here's -4, -3, -2, -1, 0, 1, 2, 3. So x is going to be on the bigger side of -5 because we need it to fall somewhere in this range in order to be on this line here. And then x is going to be on the smaller side of 3. So notice that x is on the bigger side of -5 in this statement. You can see it's on the open side and on the smaller side of 3. And that's how we go about representing our domains and our ranges when they're sandwiched between two values. You can see x is on the bigger side of -5 and the smaller side of 3. So now let's go ahead and repeat this process with the y values, okay? So now if we repeat this process with the y values, again, we're going to start with each endpoint. I notice this one pairs with -2, so I know that -2 is an important y value, and this one pairs with 4. And what I notice is that the graph uses all of these y values that are between -2 and 4. So I can leave it as a vertical number line if I want. I can also turn it horizontal if I want. But here I have -2, I have 4. I notice I'm starting at -2 and going up to 4. If you want to label some numbers in between, there's your 0, 1, 2, 3. And so I can see that x is sandwiched between these two numbers. and it is on the bigger side of the -2 and the smaller side of 4. So it's sandwiched between the two, bigger side of -2 and smaller side of 4. So again, notice that because we had two endpoints, and we noticed that x was sandwiched in between the two values, that we formed that compound inequality with an and, or a sandwich, of x between two different numbers. So let's take a look at a second example here. So again, I see two endpoints here. And because there are two endpoints, I can predict that there are going to be two inequalities in this statement. And this looks like an and because it looks like it's going to be sandwiched between two numbers. But let's take a look before we fully decide. So here, x is -3 is a starting point for x. And then here, x is 6 is an ending point for x. So I can see that x is sandwiched between -3 and 6. So I'm going to come over here and start making my inequalities, my compound inequalities. I know x is sandwiched between -3 and 6. Now if I look, x is on the, remember x is where all of the x values need to be. So we need all of these x values that are to the right, which are the numbers that are bigger than -3. So x needs to be on the bigger side of -3, but it also needs to be on the smaller side of 6. So I can go ahead and write that x is on the bigger side of -3 and the smaller side of 6. Now if I repeat this process with the y values, go here, I can see that y is -6 is an important y value. Then I'm up here, so I can see y is 1 is also an important y value, and then I can see all the y values for that graph are sandwiched in between. So I'm going to write y down, put -6 around it and 1 around it, and then really think about it. Well, y needs to be above -6 in order to make points on this graph. So y needs to be on the bigger side of -6, but then y needs to be on the smaller side of 1 because it needs to go underneath 1 here. So we can write this as a compound statement with y on the bigger side of -6 and the smaller side of 1 in one compound and statement. So let's take a look at this new example here. So this one doesn't contain any endpoints. This one contains only arrows. And remember, arrows communicate that this is going to go forever off of the screen. So you're probably looking at this without any endpoints. How on earth do we write a domain and range? Because there aren't any starting and stopping points. And that's true. We're going to take a look at what this graph is actually communicating to us. So if you look carefully at this graph, I know it's a diagonal, but if we focus just on these x values here, what we notice when this graph has arrows is that we need every single x value to make coordinates on this graph. We need x is 1 to make this point, x is 4 to make this point, x is 7 to make this point. And we're going to continue on forever because we need these points to continue drawing this graph on forever. And then the same thing happens in the negative direction. We have, x equals -3 makes this point, x equals -6 makes this point, and then so on and so forth, they continue. So essentially what we're noticing is that we need every single x value to the right and every single x value to the left to make points on this graph. And if we need every single x value to the right and every single x value to the left, that's telling us we need every single x value. And if we need every single x value, the way to denote that with domain and range is by simply writing all real numbers. So if you notice that a graph is going forever to the right and forever to the left in some way, even if it's at a diagonal, it's going forever to the right and forever to the left, and you notice that you need every single x value to make coordinates on that graph, you can simply write all real numbers. Now let's flip this around a little bit. Let's look at the y values. Again, because this graph is going up and down, I really need every single y value here. So I need this y value to make this point, this y value to make this point, and this y value to make this point, and so on and so forth. And the thing is, this graph is continuing on forever up and down as well. It's at a diagonal, but it is going forever up and down. And so as a result, what I'm finding is that I need every single y value as well, because this graph is going forever up and forever down, and eventually I will use every single y value. And if that is the case, we simply write all real numbers. So if you have arrows, you can actually start looking for instances where you may need all real numbers to make that graph. So let's take a look at this example here. The first thing I notice when I look at this graph is that I have two arrows. And because I have two arrows, I know that all real numbers might be a part of it because those arrows communicate that this graph goes on forever in both directions. Now, I know it might be tempting to write all real numbers for both domain and range for this problem. However, that's actually not the case. We have to be a little bit more careful. So here, let's take a look at everything very carefully. So if I take a look at the x values here, I notice that this graph is going horizontally left and right. So this graph is going forever to the right and forever to the left. If the graph is going forever to the right and forever to the left, it means I'm going to need every single x value to make points on that graph, because I need this x value to make this point, this x value to make this point, this x value to make this point, so on and so forth. So if I need every single x value, I can in fact write all real numbers. So now let's take a look at the y values here. Let's take a look at the y values. So let's erase our notes and let's take a look at y. Now, what I notice here is that this graph is not going forever up and down. Really, truly, the only y value I need is the y value right here, because the graph doesn't tilt up or down. So I don't need any of the y values up here, and I don't need any of the y values down here. I just need this one single y value here of 4, because all of the entire graph is at y equals 4. So for that, if I notice that there's only one value that I need for the range, I only need one y value, I can simply write y equals that single y value, which in this case is 4. So the graph is going forever left and right, making my domain all real numbers. But because it's not going forever up and down and it only uses that one value, for the range we would just write y equals that single value of 4. So now let's take a look at this one. So this one, what I notice is if I'm going to find the domain, remember the domain are all of the possible x values that I need to make points on my graph. My domain, the graph is not going forever left and right. The graph is just a vertical line going up and down, and this hidden value right here, which I can deduce is -3, is the only x value that I need to make points on my graph, because there's these x values that I don't need, and there's these x values that I don't need. -3 is the only x value that I need, and as a result, my domain is one single value, so I just write x equals -3. So that's where I start. I have one single x value that I need, so I just denote that in my domain. Now for my range, on the other hand, I notice the graph is going forever up and forever down. So I need this y value to make this point, and this y value to make this point, and this y value to make this point, and then the arrows continue on off of the screen. So if that's the case, if the graph is going forever up and forever down, my range is simply going to be all real numbers, because I need every single y value that exists to make points on my graph.